Good afternoon, everyone. Happy Friday. Welcome to the TVE Happy Math Hour, our weekly interactive math reviews for Math 1314 and Math 1324, presented by Yvette Chuca, Ruben Carizales, and Albert Isasi. Our session will be starting soon. This session will be recorded so that you may come back to it later if you need, and so others who may have missed out on today's events will be able to come and watch it. Thank you. So now, at this time, please mute your mics for the best sound experience, otherwise the feedback could interfere with information we will be sharing. We'll be sending the 1324 room link on the chat so that you may connect to your session if you're here for Math 1324. Without further ado, I'll pass it on to our presenters.
Hello, everyone, and thank you for joining us again for this Friday Happy Math Hour session. We'll give a couple of seconds for those who are here to review for Math 1324 to go to the other room. All right. Very good. All right, so let's go ahead and get started. So for today's session, we want to review for the exam too. So some of you may be taking the exam pretty soon, or maybe you have a take-home exam, or maybe you'll take it after spring break. But whatever the case is, let's go ahead and review chapter 2 with all of you. So first, let's look at a section from 2.6. So 2.6 is all about rational expressions. So it's these functions that are fractions. So there's several things that we need to look at in order for us to be able to solve some of the questions that you'll be seeing. So first, we need to know that what the domain of the function is, and of course, since this is a fraction, what we never want on the denominator is for the denominator to be equal to 0, or that the expression gives us a value of 0. So we need to determine the domain of the function. And so if we don't see it, you can set the x plus 3 is equal to 0 to find out if there is an x value that will give us a 0 for this function. So here, if we solve for the x plus 3, we see that x cannot be equal to -3, because if we put a -3 in our function, we're going to get a 0 on the denominator. So -3 plus 3 will give us 0. So for the first one, to state the domain of the function, the answer is going to be this fourth one, right? So all real numbers except the value at x is equal to -3. Now we need to be able to identify all intercepts. So just to review, to solve for the x-intercepts, we're going to set the y value equal to 0, right? But let me here go forward a little bit. And again, everything's on this slide, everything that I just said. So let me go ahead and traverse through it. So our domain is this last one, our real numbers, except for x equals to -3. Now again, to solve for the x-intercept, as I mentioned, we set y equal to 0 and solve for x. So everywhere we see the value for y, again, f of x had replaced the variable y. So we set this is equal to 0 and then solve. So to do this, we multiply both sides by x plus 3. So when we do this, we see that we get 0 is equal to 1, and we know that this is a false statement. So hence, what this is telling us that there aren't any x-intercepts. And again, in the computer, we would put as DNE, which means does not exist, right? Okay. To solve for the y-intercepts, we'll set x equal to 0, and then we solve for y. So here we have 1x, so we plug 0 for x and simplify. So 0 plus 3 is just 3. So we have a y-intercept at 1/3. So when x is equal to 0, our y value is 1/3. Okay. All right. Now we need to see if this function has any vertical or horizontal asymptotes. So let's go ahead and look at the vertical asymptotes. So Remember that the vertical asymptotes having to deal with any x value that will make our function not exist, right? So we do have a vertical asymptote, and we solve that, right? When we solve that, when we solve for the domain, right? So when we saw that the domain, we cannot put the value of x is equal to -3. This, in fact, is the equation of a vertical asymptote. At this value, the graph cannot cross or touch this imaginary vertical line. Okay? Now, and then we represent on our graph, we represent asymptotes as a dashed line. Of course, here on our slides is they look dotted, right? But on the computer and for our web assigned homework, we're going to represent these as dashed lines. All right, now for the horizontal asymptotes. So for horizontal asymptotes, we have three different cases, right? That our functions can fall under. So the first case is if the degree of the numerator is smaller than the degree of our denominator, then there exists a horizontal asymptote at the equation y equals to 0. The second case is if the degree of the numerator is equal to the degree of the denominator, then we have a horizontal asymptote at this ratio, the division of the leading coefficient of the for the numerator and divided by the leading coefficient of the denominator. And our third case, if the degree of the numerator is greater than the degree of the denominator, then there exists no horizontal asymptote. And of course, if we have this case, we know that our function will have a slant asymptote, but we'll cover that in a little bit. So let's go back and look at our problem. So we can see here that our problem falls under the first case. The degree of the numerator is 0. Okay, let me see if I can pull out my pen. So we can have x to the numerator is equal to x to the 0 power, because anything to the 0 power will give us 1. And we know that the denominator, the degree of the denominator is 1. We don't write the 1 here, but this is what we have. The degree of the numerator is smaller than the degree of the denominator, so hence we have a horizontal asymptote at y equals 0. And again, we represent this as a dashed line, this horizontal line, which is in blue. And this is, again, these are features that are going to help us be able to better understand our graph or our function. Okay, so let's go ahead and put everything together. We know that we don't have an x-intercept. We have a y-intercept at 0 and 1/3, or y equals 1/3. We have a vertical asymptote at x equals -3, and we have a horizontal asymptote at y equals 0. So in order to help us aid with the graph, let's go ahead and plot some additional points. So let's go ahead and graph we have our vertical asymptote at x equals -3, and let's get some additional points. So since our vertical asymptote is at -3, let's pick some points um, that are around our vertical asymptote. So first, let's pick it x equals -2. So we plug in x for -2, we get a y value of 1. When we pick a value for x equals 2, we get a y value of 1/5. So now let's look at the left side of the vertical asymptote. So let's pick x equals -4. So when we plug in x equals -4 to our function, we get our y value of -1. When we plug in x equals -5, we get a y value of -1/2. So let's go ahead and plot some of these points. Right? So again, our asymptotes are going to help us as far as the behavior of the graph. So when we try to plug these in, we try to do a smooth line, okay? And we know that the graph is very close to our horizontal asymptote, does not cross it or touch it. And then it's getting close to our vertical asymptote. Then again, the graph is not going to cross or touch. Then we jump over to the other side. And again, our graph comes very close to our vertical asymptote, did not cross it or touch it, and is getting close to our horizontal asymptote, where it's not going to cross it or touch it. And we have these smooth lines. Okay? So again, in our homework, they make it very easy for us to determine which is the graph because we have a multiple choice. So we looked at the options here, and um, from the options given, okay, um, I believe it's easy to say. So again, one of the options would be, okay, I know it's going to be this first one. If I label them as, let me label them as A, B, C, and D. Okay, so I know based on the graph, it looks like it would be um, A. Well, I don't know about you, but the only one that looks like it could be the answer is A. I was thinking maybe this one, but they're opposites, right? They're not in the correct position. So um, again, we can see that our answer only is for this one, which I called A, right? Very similar to what I graphed. So, all right, let's look at another example. Let's look at this function now, 3x plus 2 over x plus 3. Again, and we'll go through the same process. First, let's find the domain of the function. Again, we do not want the denominator ever to equal to 0. So um, we see that here. Again, we have as a denominator x plus 3. And if we don't see it, let's set it equal to 0 and solve for x to find out if there is a value that will give us 0 at the bottom. And we see that it does. That if we plug in negative 3 for x, negative 3 plus 3 will give us 0. So again, um, we won't be able to um, use negative 3. So now we know that our answer is all real numbers except for x equals negative 3, right? So it's this B one. All right. Let's go ahead and solve for the x-intercept. So to find the x-intercept, again, we set the variable y equal to 0. And then we solve. We're going to multiply both sides by x plus 3. When we do this, we're going to get 0 is equal to 3x plus 2. We're going to subtract 2 on both sides. It's going to give us negative 2 is equal to 3x. And divide by 3 on both sides. So we get this value. X is equal to negative 2/3. So this is our x-intercept. So let's go ahead and solve for our y-intercept. Set x equal to 0. So when we do this, we have 3 times 0 plus 2 over 0 plus 3. When we simplify, we're going to get 2/3. So our y-intercept is 2/3. All right, let's look at our vertical asymptote. Again, we already have the equation of the vertical asymptote when we try to solve for the denominator, or to see if the denominator gave us a value of 0. So we saw that when we did this, we solved that x is equal to negative 3. So hence, this is our equation of our vertical asymptote. This is the value that will make our function undefined at this point. So it creates this vertical line. Again, for the horizontal asymptote, we're looking at our cases. Um, and it's going to be this case 2, what I consider. We see that the degree of the numerator is a 1, the degree of the denominator is a 1, so they're both equal. So when the degree of the numerator is equal to the degree of the denominator, we have a ratio of the leading coefficient of the numerator divided by the leading coefficient of the denominator. So the leading coefficient of the numerator is 3. The leading coefficient of the denominator is 1. So this is 3 divided by 1, which gives us 3. So on this particular problem, our horizontal asymptote is at y equals 3. All right, so let's go ahead and use some additional points to get a better idea of the graph. But first, let's start by graphing our vertical and horizontal asymptotes. And again, these are represented by these dashed lines. So again, I will pick values around my vertical asymptote. When I get these values, when x is equal to negative 2, we get a y value of negative 4. When x is equal to 2, we get a y value of 8/5. When x is equal to negative 4, we get a y value of 10. And when x is equal to negative 5, we get a value of 13/2. So when we plot these points, again, we try to do a smooth curve, trying to follow the restrictions that we have from our vertical and horizontal asymptotes. And like I said, when we use our WebAssign, the options are very clear based on our graph. They give us a really good way to choose very clearly which one is our true answer. Again, these ones are backwards, the bottom two, and this one is way off, right? Our top one does not cross the x-axis. So again, our answer is this B part, or what I would consider the B. Okay. So again, please let me know if I'm going too fast. If you have any questions, um, go ahead and put on the chat, and I'll try to get to them. Okay. Thank you. All right. So let's go ahead and look at this next example. We have x squared minus 9 divided by x. So again, let's state the domain. On this one, we see that since the variable is just x, we know that the only variable that or number that we can't use is 0. We cannot plug in 0 for x, so now we're going to get 0 on the denominator. So the answer is all real numbers except x is equal to 0. Okay. All right. So let's go ahead and solve for the x-intercept. To solve for the x-intercept, let's set y equal to 0. So we have 0 is equal to x squared minus 9 divided by x, multiply both sides by x. This is going to give me 0 is equal to x squared minus 9. I'm going to add both sides by 9. This is going to give me 9 is equal to x squared. Take the square root of both sides. And when we do this, we're going to get two answers, right? X is equal to plus or minus 3. So we have two x-intercepts on this particular problem. We have 3 when x is equal to 3, y is equal to 0, and when x is equal to negative 3, y is equal to 0. Now let's go ahead and solve for our y-intercept. So we set x equal to 0. So here, what we see is that it doesn't exist, right? Because we have the 0 on the bottom, right? So we know that we cannot use 0 for the denominator, so the y-intercept does not exist. So let's go ahead and this is one thing you always want to try, just to double check if we can cancel anything from the numerator and denominator. So on this one, we really didn't have to worry that much, but if we factored the numerator, we can see that this is a difference of squares. We can write this as x squared minus 3 squared, which would give us x minus 3 times x plus 3. And we see that we cannot cancel any like terms. And again, you always want to do this additional step to double check if there's any values that can be canceled out. And if we do end up canceling any values, what this is going to do is going to create holes in our graph. And that's the reason why we wanted to check that we didn't have any holes or gaps in our graph. And we see that we don't. There's nothing that we can cancel from the numerator and denominator. So again, we can continue, but it's very good to always check this. Okay, so we have a vertical asymptote at x equals to 0. Now let's check for our horizontal asymptote. And we can see that on this particular function, the degree of the numerator is 2, and the degree of the denominator is 1. So the degree of the numerator is greater than the degree of the denominator. So on this particular problem, there is no horizontal asymptote. Okay. So again, this is going to happen when the degree of the numerator is larger than the degree of the denominator. So let's go ahead and try to graph this. And again, yes, there's no horizontal asymptote. There exists a slant asymptote. Okay? So to find the slant asymptote, if they would ask us to find the slant asymptote, what we need to do is we need to do a division of this function. And to better our purposes and also to practice all aspects of chapter 2, let's go ahead and use synthetic division. to divide x squared minus 9 divided by x. Okay, so here what we can see is we write the coefficients or of the numerator. So we have an x squared. Our coefficient is 1. Now we don't have an x, so we use 0. We have a constant, which is a negative 9, and we're going to divide this by 0. So when we do this, we bring down the 1. 1 times 0 is 0. 0 plus 0 is 0. And 0 times um, negative 9 plus 0 is negative 9. So we have we identify the quotient as um, this x and negative 9. So on this particular one, our slant asymptote is y equals x. Now, we could see this better just for practice purposes. We can also divide long division. I think it's better also when we see it with long division. So if I divide this by x squared plus 0x minus 9. Okay. You see here that the value that I would have to multiply to get to the x squared is just 1x. See? And this value here, okay, is going to tell us that our slant asymptote is at y equals x. Okay? So and we'll look at some other more examples. Okay? All right, so let's go ahead and plot some additional points. We go ahead and draw our slant asymptote, which is at y equals x. Um, we have a vertical asymptote at um, x equals 0. So let's go ahead and pick our points that we've been using for simple purposes. And we see here that our graph is like this. Yes, it comes very close to the x equals 0, does not cross this vertical line, and we come close to our asymptote. So when we look at our web assigned options, which is the graph that could possibly, it could either be B and C and D, but we can see that the only option that mimics our graph with our points is this one right here. It's what I would consider the C one, right? All right, let's go ahead and move forward. Let's look at this problem here. And again, this is straight off your homework. Describe the left-hand and right-hand behavior of the graph of the polynomial. So the first thing that we want to see is that the degree of this polynomial is 3. So then because the degree is 3, then this makes this polynomial an odd function. Since 3 is an odd number, then this is an odd function. So I know that the behavior is either going to fall on the right and rise on the left, or fall or rise on the left and fall on the right based on the leading coefficient. So on this one, we see that it's an odd function, and we also see that our leading coefficient is a positive number. So then what this means is we know that this graph is going to fall on the left and rise on the right. So the two options that we're going to pick are these two. The graph falls. Well, let me go ahead and give you what I just explained, that it's from the book. When we see that it's an odd function, it's going to be this, right? It's going to go up on the right, fall on the left, or it's going to go up on the left and fall on the right. Again, we see that our leading coefficient is a 12, so it's going to rise on the right and fall on the left. So when we go back, we're going to pick these two. The graph rises to the right and the graph falls to the left. Okay? So let's review multiplicity. So the multiplicity has to do when the graph either crosses the x-axis or just touches. So in this particular one, the first one here, x squared, we see that the graph touches 0 and then goes up again. So what this means is we have a double 0 here. Okay, so what this means is that we have a multiplicity. It repeats, and it's a multiplicity of 2. Or an even multiplicity. On this odd function, we see that the graph crosses the x-axis. So this is an odd multiplicity, right? So because the graph crosses the x-axis. So uh, to read more on rational expressions, we could also find all the possible zeros that a rational expression function may have by doing the rational zero test. And the rational zero test says we grab the factors of the constant divided by the factors of the leading coefficient. Um, and by doing this, we get all of the possible zeros. So let's look at an example of using the rational zero test to find all the possible zeros that a function may have. So if we look at this function, x cubed plus x squared minus 9x minus 9, we see that our constant is a value 9. Again, I am not interested in the sign of the value of the constant because I'm going to be looking at all the factors and I'm going to be looking at the positive and negative factors of 9. So I'm not interested that it's a negative 9. I'm going to divide these by the values by the factors of the leading coefficient. And in my case, the leading coefficient is a 1. So I'll be looking at all the factors of 1. So when I do this, again, I'm using shorthand notation to look at the factors of 1, 3, and 9, which is plus or minus 1, plus or minus 3, plus or minus 9, plus or minus 1. But when you're putting them onto the computer, onto WebAssign, it wants it as a list, and there's no symbol for plus or minus on the computer. So unfortunately, you have to do it the long way. You're going to have to write, when I do the divisions of the positive 1 by 1, the positive 1 by the 3, the positive 1 by the 9, and then the negative 1 by the 1, the negative 1 by the 3, the negative 1 by the 9, we get these answers. We get negative 9, negative 3, negative 1, 1, 3, and 9. These are all the possible zeros. Again, it's a test. It could be true that some of these are zeros, and it can not be true that some of them are zeros, or we can get that none of them are zeros. Again, this is a test. Just I always tell my students jokingly, when you got a COVID test, you had two answers. Either it was positive or negative. So in our case, this is a test. We can either get a zero or not get a zero. Okay, it's just a test. And we can see also that this function should have at most 3 zeros, and the test gave us an option of 6 zeros. We're not going to have this many. So again, it's just a test. It's to find or discover the possible zeros. All right, so we want to use the possible zeros because now we're able to use synthetic division with a more accurate choice of numbers. We don't want to choose numbers blindly to find the true zeros. The rational zero test will give us a small number of values to test, to find if they are zeros. So let's go ahead and again practice our synthetic division. And let's choose our first possible zero, 1. So we bring down the 1, we multiply by 1. 1 times 1 is 1. 1 plus 1 is 2. Um, oh, um, and 1 times 2 is 2. So negative 9 plus 2 is a negative 7. And 1 times negative 7 is negative 7. And there is a typo here. So again, this value should have been, let me fix this really quick. This should have been negative 9. So negative 9 plus a negative 7, this should have been a negative 16. But what we need to know is that 1 is not a factor of this. Since the remainder was not 0, 1 is not a 0. Okay, so let's go ahead and look at another example. Let's try the negative 1. Again, let's bring down our 1. 1 times 1 is negative 1. Negative 1, 1 minus 1 is 0. 0 times a negative 1 is a 0. So negative 9 plus 0 is negative 9. And negative 9 times a negative 1 is a, a positive 9. But this one is negative. This one is correct here. Let me put in my negative. So we see that negative 9 plus 9 is 0. So since the remainder was 0, we're happy about that. But that tells us that negative 1 is an x-intercept, that the graph is going to cross at x equals negative 1. Okay, so it is a 0. All right, so when we have this, it makes our life easy because we can get our quotient, and our quotient becomes x squared minus 9. So now having this, we can either factor it, we can use our quadratic equation to find the remaining zeros. So if we solve for the x, okay, we can use our square root property and take the square root of both sides. And we see that x is equal to plus or minus 3. So we've got all our zeros, right? We have 0 is equal to x equals -1, x is equal to -3, and x is equal to 3. And this is accurate, right? We saw that this function had at most 3 zeros, and we do. We have 3 zeros for this one. It's good to know or to practice on some homework problems. You are asked to write the function as a product of linear factors. So these are the factors that are produced from -1, -3, and 3. The linear factors are x plus 1, x plus 3, and x minus 3. Okay. All right. So let's go ahead and do this example now. Let's go ahead and list all the possible zeros for this function, which is x to the fourth minus x cubed minus x squared. Okay, let's do this a part first. We're going to, um, well, um, find a possible rational zero using 0. So let's go ahead and do this one now. Um, Again, if you see here, my zeros here, I'm replacing them because I don't have a x value and I don't have a constant, okay? So I have the 1 for the x to the fourth, the -1 for the x cubed, and the -6 for the x squared. So when I solve for this, okay, I see that my quotient here is x cubed minus x squared minus 6x. Now what I can do is I can repeat this process because again, it would be really hard to factor this because it's a cube and there is no formula to solve for x-intercepts when we have a cube. So what we can do is we can use synthetic division to repeat this process to go ahead and see if we can simplify this any further. So let's go ahead and divide by 0 again. Okay, so when I divide by 0 again, I get now a squared. I get um, x squared minus x minus 6. So now that I have a square, I believe this would be easier to factor or to solve our quadratic equation. Again, for me, factor is always the way to go, but if we don't see it, we can use our quadratic equation. So let's practice that. Let's practice our quadratic equation. Again, the quadratic equation is to find the x-intercepts of a function, and it's given by minus b plus or minus the square root of b squared minus 4ac all over 2a. So I see that my a value is 1, my b value is -1, and my c value is -6. When I plug these values into my quadratic equation, I'm going to see that I have two x values, x equals 3 and x equals -2. And again, I would have factored, but it's good to always practice the quadratic. So on this particular problem, um, our zeros, we have a multiplicity of 2 for x equals 0 because we have two zeros. And then we have a multiplicity of 1 for the -2 and a multiplicity of 1 for the x equals to 3. So if we were to determine the maximum number of turning points, okay, there is a formula to solve that and to find or determine the number of turning points is the degree of the function minus 1. So in my case, the degree of the function is 4. So 4 minus 1 is 3. So this one has 3 turning points. Okay, so if we're to plot, again, also using our left hand and right hand behavior, we see that it's an even function. So we know that it's either going to rise on both sides or fall on both sides, but we know that it's going to rise on both of the sides because the leading coefficient is a positive number. So the graph is going to go up on the left and up on the right. Okay. Um, and we use our intercepts. Now, if you really want, yes, go ahead. Okay. Yeah, and guys, if you have a question, go ahead and speak out or go ahead and put it on the chat, okay? So if we really want to see what's going on between our intercepts, we can pick additional points. So here I picked up -1, 1, and 2 to see the behavior of the graph. And if I try to do a smooth line of this graph, I get something like this. But again, if I were to plug it into my graphing calculator, I see that I have this much nicer graph that is almost identical, right? Almost identical to mine. But again, this is also just to help us on answer a multiple choice graph, answer for the graph. Okay. All right. So let's look at this problem here. Use a given zero to find all the zeros of the function. So they give us this function x cubed minus 12x squared plus 52x minus 80. So I know that I could possibly have up to 3 zeros for this function, and they give me one of them already. They tell me that one of the zeros is 4 plus 2y. So what I can do is I can use synthetic division, and yes, you can use synthetic division with imaginary numbers or complex numbers to see if we can reduce this in order to help us find the remaining zeros. So again, here I'm going to use synthetic division with my complex number to reduce this function. So let's go ahead and do this. So when I bring down the 1, 4, excuse me, 4 plus 2y times 1 is 4 plus 2y. Okay, and I wanted to do this also so we can practice the addition and subtraction of complex numbers. Recall that to add or subtract complex numbers is just you're going to add the real with real and imaginary with imaginary. So the -12 does not have an imaginary, so that's plus 0i, but I have a real part on this complex number, the 4. So the -12 plus 4 is going to give me the -8, and the 0i plus 2i is just the 2i. So then I do the multiplication again. Okay, I use FOIL to multiply these two complex numbers. Let's go ahead and combine like terms and simplify. And when we do that, we're going to get minus 36 minus 8i. Okay, so when we add again these two numbers, we're just going to add the real with real, imaginary with imaginary. So 52 minus 36 is going to give me 16 minus 8i. Then I'm going to do it the same. I'm going to multiply 4 plus 2i times the 16 minus 8i. I get this complex number. Let's go ahead and simplify it by combining like terms. Um, and we know that I squared is equal to -1. So a -16 times a -1 is going to be a positive 16. So 16 plus 64 is going to give me 80. So here we reduced our quotient to this, x squared plus -8 plus 2ix plus 16 minus 8i. Okay, so this is still a little too complicated to solve for the x-intercept. So let's go ahead and do it again. Let's use synthetic division to simplify our function better, right? So we'll do the same process again. And when we do it again, our quotient is a lot better, right? We get this. We get x equals x minus 4, which is going to give us x equals 4. Okay, so now we have um, another 0. So we have our 3 zeros, x equals to 0, and then we have our 4 plus 2i and the 4 minus 2i. Okay. All right, let's look at this one. This one is a little bit complicated to solve. It says find the polynomial function with the real coefficients that have the given degree, zeros, and solution point. Okay, so again, the degree of the polynomial has to be 4. Um, and then they give us these zeros. Well, what these zeros mean, okay, if I were to solve it, they're saying that x is equal to -4 is a 0, at x equals 1 is a 0, and at x equals I is a 0, okay? But we know that the I came from a square root, just like the previous problem. Um, we know that there's two answers for this. We have the positive I and the negative I. So the factors, if I convert these zeros into factors, we have x plus 4, x minus 1, x minus I, and x plus I. Applying what's called my linear factorization theorem says that if I multiply all my linear factors together, I'm going to get back the polynomial. So that's what I've done. I'm going to multiply all my linear factors, and again, I have a a sub n, this leading coefficient that I still don't know what this value is. And we're gonna find this value by using our solution point. But let's go ahead and first multiply our linear factors. So um, so the first thing that I did is I multiplied the x minus I times the x plus I. So here I'm going to combine like terms, and then I'm going to simplify. I squared, I know, is equal to -1. So we have x squared plus 1. Let's go ahead and continue the FOIL. Let's pick another one. Let's multiply the x minus 1 times the x squared plus 1. Combine like terms and simplify. Then now we have x cubed plus x minus x squared minus 1. Let's multiply by the last factor, the x plus 4. We get this long equation here. Let's simplify and by combining like terms. And I like to also put it in general form, which my leading coefficient, the degree of the equation is the largest first, and I write the rest in descending order. Okay, so I have x to the fourth plus 3x cubed minus 3x squared plus 3x minus 4. But what about this a sub n? Now this is where the solution point is going to come in handy. This is telling me that when x is equal to 0, I have a y value at -8. So that's what I'm going to do. That this says that when I plug in a 0 for x, my answer should be -8. So let's go ahead and simplify. And when I do this, I'm going to get -8 is equal to a sub n times -4. So to solve for a sub n, I'm going to divide both sides by -4. So a sub n is equal to 2. So the polynomial with these characteristics, and if you can see, the degree is of 4. That's the largest exponent. With these zeros and with this solution point, I just have to replace a sub n by 2. So I got to distribute this 2 to this long polynomial. So when I do that, I'm going to get 2 to the x to the fourth plus 6x cubed minus 6x squared plus 6x minus 8. Okay, so this is a very popular exam question. Okay, hint, hint, hint. So I'm at the end. Does anybody have any questions for me? Would like me to go back and review something that I didn't cover? Um, okay, well, if not, um, then I'll end our session early. Again, thank you again for joining me today. Again, please remember to go ahead and log in and click on the link to get credit for attending today's session. For those of you who your instructors are giving you extra credit, or you need a credit for tutoring as a grade for your overall class grade. Please give your evaluations to us. Tell us how we're doing. We love to hear um, what we can do better for you all. So please don't forget to click on the links. I want to wish you all a happy spring break and good luck on this second exam. So I want to remind you that we have excellent tutors. If you want to stick around, you can visit one of our excellent tutors to go over in more detail any materials covered or anything that I didn't cover. Okay. So again, thank you all for joining me today, and I wish you luck and stay safe and enjoy your spring break. We'll see you again when you guys all come back in a week from today. Okay. Thank you all.
Thank you, Mr. Carizales, for your presentation. We do want to remind everyone about our previously recorded sessions, which are available on a YouTube playlist. This session will also be available on that playlist later today. Also, link to this short survey to help us improve our TVE sessions. Please take a few minutes to fill out that survey and the other short survey to receive credit for attending. Thank you all for coming in today. We hope you have a lovely weekend. But before you all leave, we want to share the TVE sessions that will be available the week after spring break. Okay, so the Friday after spring break at 1 p.m., we will have Prep to Rank, a presentation from EPCC's Prep program. And at 3 p.m., we will have our Happy Math Hour again with 1314 covering exponential and logarithmic functions, and 1324 covering systems of equations. Thank you all for coming in today. We hope you all have a safe and relaxing spring break. If you guys have any questions or anything to add, feel free to use your mic or the chat box. Thank you all for coming in today.